First, can you share about your personal journey in data science and machine learning, like how you developed your skills and expertise in this field?
Yeah, so I started learning data science sometime in 2011. That's when I started learning. It was a personal interest out of which prior to that I was into C++ programming. So where I've done, I was working with CA technologies, and we've done some interesting work on compilers and a lot of good stuff on core programming stuff. Then 2011, I found interest in statistics and data science, and that's how I got started. In around 2013, I shifted totally into data science with CA technologies, and slowly from there shifted into Providence now. Almost two
Yeah.
and a half years there. So that's short description of the journey. So yeah, you can ask the questions and then.
Yeah. Yeah. So I mean that's really nice. Like you're coming from a core computer science background and then shifting into statistics and data
Yes.
science. But yeah, so also we like in a previous meeting with our batch earlier and yeah, in your LinkedIn profile as well. So you mentioned that you're interested in like your interest also lies in topological data analysis and quantum machine learning. So these two are totally niche topics and into deeper mathematics and computer science as well. So how would you say that like what inspired you to pursue research in those specialized areas?
So I was trying to. I love mathematics basically. So that's how I got into machine learning in the first place. And along the way, I started learning a little bit of, as I started exploring mathematics, I found quantum computation to be very interesting from math angle. So from the perspective of
Yeah.
mathematics, it's so I don't study it from physics perspective. I don't know physics basically. So I studied from math angle, and I found it very interesting. Even prior to that, during my studies itself, I was into computational theory of computation basically. So
Yeah.
I loved that subject. So I just linked these two. So and found the most interesting area to be topological data analysis and quantum computing. Basically, I do independent research on theoretical quantum computation. Basically, I do it on
Okay.
applications of basically hidden subgroup theory to
That's
quantum world. Yeah, that's
that's really fascinating. So I myself come from a mathematical background from CMI. So
so nice.
yeah,
Yeah.
yeah. So like we also had in our curriculum algebraic topology in our undergrad and as well as in the masters. So the thing is, in like we have that theory of homology, right? Wherein we can actually count the number of holes in some topological spaces.
Correct.
I just want to know how like this whole detection formalism of algebraic topology can be like connected with this robust computational methods to extract qualitative features in data.
Okay, so the area that I study, basically, the area where
Yeah.
I research is called hidden subgroup problem, which is basically, as you are into maths, right? So you might have studied algebraic topology cannot be learned without the algebraic fundamentals, right? So you might
Yeah.
have
Yes.
studied the group theory and stuff like that. So there is a particular result in quantum computation which says that if there is an abelian group basically, right, it is easy for a quantum computer to compute the generators of a hidden subgroup in that abelian group.
Yeah.
Let's say, so there is a subgroup called H which is, let's say, hidden. I want to find the generators of that. It's easy. So most of your computational advantages that you found in quantum computing, for example, you might have heard about the Shor's algorithm, the
Yeah.
elliptic curve cryptography algorithm, and all these things. All those that give you an exponential speed up are basically instances of this abelian hidden subgroup problem, basically.
Okay. Yeah.
And then there are other problems which are close to this, like dihedral group and all, which are not abelian group, but there are some speed ups possible in that. This is the quantum computer result, basically. Now,
Yeah.
as you know, hidden subgroups are also present in this algebraic topology, because algebraic topology is also about
Yeah.
hidden subgroups, right? So you're basically talking in terms of groups. Basically, you talk about quivers, basically, where you have you construct the homologies, persistence and
Yeah.
homologies, and this is the subject. And the same kind of groups are also available in the other side. So my exploration is, can we do a speed up on those, right? So we do have one result on topological data analysis, which is very famous by the Seth Lloyd, I guess, LLOYD, Seth Lloyd. So which is on, which uses more traditional quantum computing, non-algebraic quantum computing. So he does start with the study of topological spaces and all that, but he doesn't do it with from algebraic perspective. So that's where I started. So the way I entered into this is just out of curiosity and exploration. So math excites me. So machine learning excites, and this also excites. So that's the essential feature, basically. But topological data analysis is very powerful. One of those areas which you not the out of the box algorithms, but probably the internals of it can be used in your day-to-day data science as well. That's my perspective.
Oh, okay. Oh, that's actually nice to hear, because I mean, what we have seen in theoretical sciences, like it's really difficult if you go into those niche topics to connect with reality. And yeah, I mean, many of my friends back in my undergrad days, they also like, I mean, they didn't know how to connect those theory with, some applications in real life. So like, is there any like real-time applications of topological data analysis that has been going on in industry?
So there is a entire company spun out of topological data analysis called IHD, right? You can Google it out. That's a very interesting. They started with topological data analysis, but I am more see. There is one problem with topological data analysis. If you think about it, your graphs, right? You have edge node graphs that you talk about. Now, those are one-dimensional topological objects, right? So they're nothing more than single-dimensional topological objects. So when you take a graph, so in our machine learning, we have probabilistic graphs where each node is represented with a probability distribution, right? So that's how we study machine learning, isn't it? So everything in machine learning is about these things. One, we have probability distribution, right? And then we are trying to predict something using the probability distribution, in the sense that we are trying to, in a in a rough way, we are just trying to get the averages, right, with some given certain conditions, right? So it's basically happens to be there is under every scenario we have a probabilistic graph in picture, which is either explicit or implicit. So if it could be explicit in the sense that I might actually have a physical graph and then do some analysis over that, do a variational inference or MCMC and draw the probability distributions in the Bayesian style, right? Or I can talk in terms of a deep learning algorithm, let's say, to the other extreme, where you have the weights are basically, we are treating them as normal distribution, and when we take an MSE or something, that's also approximating it to a normal distribution, right? So basically the graph is implicit, so you're learning so the graph is still there, in the sense that there is a probabilistic graph in picture. That's a model of data, right? So the model of the algorithm, rather, so model of what you're trying to get out of the data, because without a model, the data itself doesn't speak anything, isn't it? So it's the lens aware that makes data give us meaning, right? So that's always there. The graph is always there. Now to think about a scenario where a graph has an edge between two nodes, right? So there is a node and there is an edge between them, right? There are two nodes, there's an edge between them. How about a scenario where I want to say how blood pressure is, let's say, one node, right? Let's say diabetes is another node, right? Now, how does blood pressure and diabetes function together, right? To give how does it function together? How do they, when a person has both diabetes and blood pressure, what is their the curve that determines their let's say disease progression, let's say, right? When I talk about this, right, now I have to take not just the edge between diabetes and blood pressure. Let's say CKD is a future element, right? I have to take all three together, right? That's a simplex.
That's
right. So when you take three nodes together, and that entire triangle is a simplex. Now I have to see how this triangle functions with respect to something else. So now this kind of an exploration is has a problem fundamentally inherent in it, because I can't see all combinations, right? So let's say I want to see 4-dimensional, let's say tetrahedron, and go on to 5-dimensional simplices and all that. So as I go higher and higher to the higher simplices, it becomes computationally infeasible, right? So, however, doing that has an advantage, right? Can I approximate that, right? So in so this is a theoretical framework for you now, right? So you understand this from the perspective of mathematics, right? Now comes engineering, where you break down problems in such a way that you can do this analysis on real problems, yet not explicitly have a simplex in place, right? So that is the beauty of how you can apply this. So we have been able to do a few applications, but that then it's open, actually. The possibilities are immense.
Yeah, that's great.